Okay. Hopefully, if days 74 and 75 went well for you, today should be pretty easy because we're just going to go backwards. So we've done derivatives already. If the derivatives made sense, then the integral should be ridiculously simple, except for one small thing, which we'll get to in a second. So we're going to do integration, like I said. We're going to talk about the log rule for integration. We're going to finally get the integrals of the other trig formulas, or the other trig functions, I should say. So you'll recall, we know sine and cosine, and then we know all these other weird ones, like secant squared tangents, or secant tangent, or these other things that don't seem to make any sense. Today we're going to get all, so you'll have all six: sine, cosine, tangent, cotangent, secant, cosecant. And then you should be able to balance a checkbook. And then when I wrote this, I thought, do you guys even know what a checkbook is? Yeah. Oh, okay, good, just checking. Just checking. I didn't even plan that, but you know what, I'm going to say the same thing, 6th period, pretend I didn't plan it. Wow. Okay, so we know this. The derivative of the natural log is 1 over x. Or, what we're using most of the time on the right is u prime over u. Why are there absolute value bars in there?
Because you can't get natural log of a negative.
Good. Or?
What do you mean?
You can't take the natural log of a negative or 0. Right, okay.
Yeah.
So, what the absolute value does is, again, it's a little bit of cheating, and we're just saying, I don't want to have to worry about whether or not I'm plugging in a negative number. We do have to deal with 0, but we'll skip that for a second. I'm just going to make it absolute value, and then by making it absolute value, I guarantee I'm putting in a number that actually works. If I'm putting a number that doesn't work, then we're done. You can't do anything with it. Okay, so again, that's review. But if the derivative of the natural log of the absolute value of x is 1 over x, what's the integral of 1 over x? It's not a trick question.
So it's next to the
If I'm taking the derivative of the natural log of x, and I'm getting 1 over x, what's the integral of 1 over x? Natural log of x. Okay, we're done. Have a nice day. No, it's a little more complicated than that. But yeah, that's what it is. And we get the absolute values in there. That's the biggest thing that you have to remember, is those absolute value bars are needed most of the time. We'll talk about when they're not in a second. And then the other problem that's going to come about here is remembering how to do integrals, like UDUs.
For TV, she's special.
Wait.
This is like a sick joke.
Oh, good, there we go.
All right, we're good.
Put it on your
Okay. Okay, so antiderivative of 2 over x. How are you going to approach that problem? Yeah, move the 2 out in front. It's in the way. Nobody cares about it. Put the 2 out in front. I like it. What's the antiderivative of 1 over x?
natural log.
Natural log of?
X.
Of?
Absolute value.
Absolute value of x. Plus c. Very good. We're done. Yes, it's just that easy, kids, for that problem. Why a plus c?
Indefinite integral.
Indefinite integral, no limits of integration, blah, 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 blah. Ooh, then I got all fancies in my fancies. Can you stop in the second line? Is 2 times the natural log of the absolute value of x plus c an acceptable answer?
Yes.
Yes, it's fine. But if you want to show off, then you could bring that 2 out in front into the thing that you're taking the log of. Where'd the absolute value bars go? Yeah.
You're squaring it so it has to be positive.
That'll happen occasionally, that you'll get a value that can never be negative, so therefore the absolute value bars are not required. If you're not sure, leave the absolute value bars there. If I was to enclose that an absolute value, nobody's going to mark that wrong. It's fine. But if it's an answer that requires absolute values and you don't have it, then there's going to be a problem. Okay, so you understand the difference there? Good. All right, so that's what that says. Okay, now we're going to ramp it up a little bit. What the hell? Okay, what do we do? Other than cry and cheat and pray and drop the class and all the other options we normally. Suggestions? Nope.
You can factor out next from the bottom.
Factor out an x at the bottom, then what?
And then your bottom front is 1 over x. Or you could do that and then times 1 over x.
But remember, the limit. It's been a while for me to. The integral of a product is not the product of the integrals. So if I factor out an x, I can't do the integral of 1 over x times the integral of the other gunk that's left behind. Good?
Or you just do u du substitution.
Just do u du like it's no big deal? All right.
Be x cubed plus 3.
Whoa.
Whoa.
What do you want to use as u?
X cubed.
Whoa.
X cubed plus 3.
U equals x cubed plus 3.
Yeah.
Where'd the 4 go?
It's still there. So it'd just be 4. Oh wait, no. Never mind.
So put the 4 back. You want to use that?
No, because then that would have to the bottom.
I think we've talked about this before, but the rule when doing a u/du is, in a situation like this where you have a rational function, most of the time if you're going to have a u that works, you take the higher degree. So if this is a u/du problem, then we would choose x to the 4th plus 3x. All right, try that. See if that works. Set it up. You should be able to solve it based on what we've talked about, if that is in fact the u value that we're going to use.
Oh yeah.
Plus it'll act as a good refresher on doing u/du since it's been a couple weeks.
Does it just equal 0? They can't.
Yes, sir. That's how I do it.
That's just 4x cubed plus 3. And then you just take the.
Did Tim pick a good u?
Yeah.
X to the 4th plus, I picked that one?
Yeah.
Did Reedy pick a good u?
Yeah.
Beautiful. Lauren, what's du equal to?
du is 4x cubed dx plus 2 du. Like,
You got extra dx in there.
oh, plus 3.
Okay. Jen, I don't know what kind of voodoo you learned from the other guy. Was it Grassy or Helene? I don't know what kind of weirdness he taught you there, but the way we do things here is you solve for dx. Did you solve for dx? In other words, does this look familiar? Okay. We'll get on board the party train, sister. That's how we roll. Question? Answer. What were you going to tell me?
Well, then the top and the bottom cancel out now.
So again, depending on how comfortable you still are with the u/dus, you could go whoopsh, whoopsh, and this becomes the integral of 1 over u, whoa, 1 over u du. Easy peasy lemon squeezy. What's the integral of 1 over u?
ln u.
Natural log of? No. Absolute value of u plus c. Which means we have the natural log of the absolute value of x to the 4th plus 3x plus c. Pregunta.
Would we always like something like 1 over?
I never use terms like always and never.
Okay, classic.
Anybody? You with me on that, right? What was your question, Sam?
Well, it's like, how would we like find like when it's like not 1 over u or 1 over x, like natural log of something? So like, how would you like go?
You won't get a natural log as an answer to an integral unless it's a 1 over something.
Okay.
Yeah, because that's what the theorem says.
Okay.
We good on this? Problems? Outstanding. Let's move on. How could we make it more interesting?
Trig.
We could use trig. I didn't, but we could.
I thought
Okay,
it was-
because the reason I did this because we're going to get to trig later on. We could make the the function more complicated.
Square root.
Or I could give you an example that looks like it's impossible.
Sure.
Okay, I don't have to. I did.
I said that do it though.
Well, it does, but it doesn't. So splitting the fraction, we've done that before, but usually when we split the fraction, the numerator has 2 terms in it. Now we've got 3. And this one gets even a little scarier in that you have to split the fraction in a weird way. And I'm just going to take you through this so you've seen it. This is a kind of an extreme case. In other words, we could write that as the integral of x squared over x squared plus 1 dx plus the integral of x over x squared plus 1 dx plus the integral of 1 over x squared plus 1 dx. Yeah, that ain't gonna work. Okay, we're gonna run into some problems there. So how do you do it? I'll show you. Factor it? Do tell. Okay. Here's what I'm going to do. I'm going to rewrite it in this form. All I did is switch the 1 and the x, which I can do because addition is commutative. Then, all right, now this is the first one that we've done where, I think it's the first one, we may have seen others, but the first integral on the left there is easy. Because what's x squared plus 1 over x squared plus 1? 1, and the integral of 1 is x, okay? So that's, boom, done. I need a plus c, but we'll deal with the plus c at the end. The second one, however, is a u du. What's u? Good. So this u is going to apply only to this, x squared plus 1. So du is equal to 2x dx. So dx is equal to 1 over 2x du. The x's cancel, I'm happy. And that's plus 1/2 times the integral of 1 over u du. I lose anybody there? We good? No as in I didn't lose you, or no as in you're not good? Yes. No? I'm just going to keep going then. X plus 1/2 times the natural, whoa, not an h, natural log of the absolute value of u plus c, and therefore we get x plus 1/2 times the natural log of the absolute value of, what's u? X squared plus 1 plus c. was fun. Now, if you're feeling saucy, you could move the 1/2 back under the, behind the natural log and turn it into a square root thing, but I'm just gonna leave it like that. Those aren't very common, but when they do pop up, I want you to be able to solve them. Because notice, if I choose the numerator to be u, it doesn't work out, nothing cancels. If I choose the denominator to be u, it doesn't work out, nothing cancels. So I have to come up with another alternative, I have to come up with an alternative approach to solve the problem. And this splitting the fraction in a weird way is what's going to work for us. Okay? What else can we do? Trig. Ooh, I wrote right over that. Let's do that first. Before you get started in there, let's review what a differential equation is. I'm telling you that the derivative of some function y is equal to 1 over x, natural log of x. What am I asking you to do? Nope, already took the derivative. Say again? Take the antiderivative, right. I want to know what y is. Solving the derivative, the differential equation means you're solving for what the actual original function is. So take the integral of both sides. Go ahead. This will be good practice. You are right. That's the derivative of x would be 1 if I can do it. Because it's going to be ln x.
Yeah.
Unless we should do break it up as in 1 over x and ln x.
It does. That's perfect. You can use a fancy board.
1 over x.
Red okay, or do you want to change color? I also have a little black. Okay, so press on the little red dot at the bottom. Okay, go crazy.
That's fine, that's my story.
So while Lindsay's writing, I'm going to do a little bit of explanation. This becomes a UDU problem, and you have a couple options for u. You can choose the whole denominator, but that turns into a scary product rule, which doesn't cancel with anything. You could choose x as u, but the problem, the derivative of x is 1, and that's not going to cancel. The secret to this is choosing u to be the natural log of x. And you can see what she did as she works through the problem to get to the answer. Her comment to me is, well, that looks a little weird. And the answer is, yes, it looks very weird, but that is, in fact, the correct answer. Well done. Let's give it up. Okay, so she takes u to be the natural log of x. The derivative of the natural log is 1 over x. And there's going to be some confusion because you're going to be flipping back and forth between the derivatives of natural logs and the integrals of 1 over x. We don't know how to take the integral of natural log. Okay, just as something to file away in the back of your brain. When you solve for dx, then it turns out that dx is equal to x, which makes us happy because that x is going to be up on top. Therefore, the x on top is going to cancel with the x on bottom, and we reduce to a nice simple equation of 1 over u du.
That's this.
Take the integral of 1 over u du, which is the natural log of the absolute value of u, sub back in for u, we get the natural log of the absolute value of the natural log of the absolute value of x plus c. Okay. Questions on that? Go.
Where'd the x go in the numerator? Where'd the x go from? Denominator.
It cancels out.
Okay, so
Oh, okay, I see.
when she solved for dx, we're subbing in for dx here, so that x is up on top. It would be up here, it would cancel with it on. Normally, we get it on the bottom and it cancels with the thing on top, so it's kind of a reverse type thing. Okay. We good? Now, that's a ton of work to do something that pops up fairly frequently, so therefore, we could just write that as a theorem. There's all the word for it, blah, 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 blah. You could just remember that. It's up to you. But for some reason, this idea of x times the natural log of x, or u times the natural log of u as a denominator pops up over and over again. And yeah, you do get that weird answer of the natural log of the natural log of x. Okay, now let's, are we good? Question.
So you don't have to do the double absolute value bars underneath the...
No, because the implication is when you start the problem, since you have the natural log originally in the problem, it's already going to restrict your domain. Okay. That's a good question. I want to make sure all of you heard. Nolan just asked, well, don't you need the other pair of absolute value bars? The answer is no, because if you look at the original problem restricts x already. It says, I'm going to take the natural log of x, which means x cannot be what? 0 or negative, correct. So the original problem restricts that domain. That happens a lot in these problems. And it's something that you want to check before you start diving into a problem. What can or can't x be before I start doing derivatives and integrals and all that other stuff? Okay? All right, good. All right, let's talk about trig. Here we go. We want to know the integral of the tangent of x. We don't know that yet, do we? We know secant tangent. I think we know tangent squared. Secant squared, tangent, I never remember these things. Yeah. All right. Knowing now what we know, how would I do that integral? Tangent's the same thing as what?
Sine over cosine.
Now what? What's u? Cosine?
Yeah.
Just 50-50 shot, that's what you went with?
Yeah.
Could it be sine?
Yeah, it could be either.
I don't know. Could it?
Because they have the same power.
Okay. I don't remember which one I chose. Oh, I did cosine.
On the bottom.
Yeah, so take the bottom like we're used to. Take it through the same process that we've done with u to u problems, and lo and behold, we end up with negative 1 over u, which now you know how to take the antiderivative of. And we get this weird equation then for the integral of the tangent. That's 3 of the 6. How would we do cotangent, for instance? We're not going to, but how would we do cotangent? Same way, right? Cotangent as cosine over sine. Pick a u, go with that. How would we do secant?
Cosine.
Secant, same thing as
1 over cosine.
1 over cosine, blah, 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 continue. Without doing the other 3, we get that nice little formula sheet. So again, as much as I'm not a fan of memorizing, you have to decide, am I just going to slap these on some flashcards and practice with them to memorize them, or am I going to derive them every time that I need to take the integral of tangent? Or, let's suppose you decide you're going to make flashcards of those, put that where it belongs. I don't care, put it where it belongs. I'm on a test or a quiz and I need to take the antiderivative of the cotangent and I don't remember the rule. I can always go back to the process we just talked about and derive that formula. It's entirely up to you how you want to approach that. You do need to know all 6 of those, along with the other ones we've already talked about in trig. You might also notice, as you look at that chart, you might also notice some patterns in there that might help you remember what each of those integrals are. So for sine, we have the golf ball thing, and then cosine would just be sine. Tangent is a negative sign with a cosine, whereas cotangent is no negative sign with the sine. In other words, you'll notice if your answer has a sign in it, there's no minus sign. If your answer has a cosine in it, or all C's, you'll have a minus sign. If that helps, great. If it doesn't, then just don't listen to me. I'm sorry, what's that? Right.
Why, but for some reason.
Dumbest thing ever, right? But it works. It works for me at least. For
For
some people, when in one ear and out the other, but that's okay.
If it helps only one person, I've done my job.
We're done. Questions? Gotta go, oh yeah, that's crazy. Okay, doc.
Let me exit this, discard, come here, stop.